Okay, in this lesson we're going to take a look at how to perform function operations and something new called compositions. Operations on functions is just addition, subtraction, multiplication, and division. So the operations that you've done with numbers for a very long time, now we're going to do them with whole functions. So it's basically, for addition and subtraction, just combining like terms. If they ask you to find h of x, and h of x is defined as f of x plus g of x, then you just take the two separate functions. So here they've defined two functions, f of x equals 5x, g of x equals x plus 2, and you're going to add them together. So that's what they're showing you right below that. So right here, 5x is function f, and x plus 2 is function g of x. So you add those together, like terms, the 5x and the x get added to give you 6x. And then the 2 is the only constant, so it's just plus 2. So h of x, if it's defined as f of x plus g of x, would just equal 6x plus 2. If they ask you to do the same thing with subtraction, then you'll just subtract the two quantities. Just be sure to distribute this negative sign to both terms. So you do 5x minus x and get 4x, and then you'd have to subtract the 2 to get the negative 2. So h of x would equal 4x minus 2. For multiplication, we use all that we know about multiplying polynomials. So in this example, since f of x is a monomial, a single term, and g of x is a binomial, two terms, we can use distributive property to take 5x times x and 5x times 2, and you come out with 5x squared plus 10x. If they were both binomials, so if they both had two terms separated by plus or minus, you'd have to use FOIL or a generic rectangle in order to multiply them properly. Division, we're not going to get too in-depth with division here. We mostly just write it as a fraction. So in this case, f of x goes in the numerator, g of x in the denominator. So f of x was 5x, g of x was x plus 2, so we just leave it like this. H of x equals 5x divided by x plus 2. If they all had a common factor, we would factor that out and reduce the fraction, but we won't get into polynomial division here. Next thing we want to start to apply is domain. So we had you review domain and range prior to this lesson because of this. So the domain of h consists of the x values that are in the domains of both f and g. Additionally, the domain of the quotient does not include x values for which g of x equals 0. So there are two main things we look for when we're talking about domain, two main problems. The first one are even roots. If we have a square root, a fourth root, a sixth root, etc., we can't have negative numbers underneath, because if we have negative values under an even root, then we would get the imaginary value, or it wouldn't be possible. We don't have any real solutions to those problems. You can't square a number and come out with a negative, or raise something to the fourth power and come out with a negative. Because if you multiply something an even number of times, if it started negative, those negatives would all pair up and cancel out. So that's the first thing we look for, are even roots. Square root, fourth root, sixth root, etc. We got to keep whatever's underneath positive. The second thing we look for is division, like we have here in this last example we did, h of x equals f of x divided by g of x. We cannot divide by 0. So for this function, the problem would be we're dividing by x plus 2. X plus 2 could not equal 0, because if it does, we've got 5x, so 5 times whatever the x value is, divided by 0. Division by 0 is undefined. So if we solve this for x, we see that the problematic value is negative 2. So x could equal anything but negative 2. So the domain for h of x in that final example would be everything less than negative 2. So negative infinity to negative 2 with a parenthesis to show we can't equal it. Remember, this u is called the union. It just means to connect the two sets. Negative 2 to infinity. Okay, so a power function. So a power function has the form y equals a times x to the b, where a is a real number and b is a rational number. So we have two power functions here. F of x equals 4x to the 1/2, which remember x to the 1/2 means the square root. So another way of saying this function, another way to write it, f of x equals 4 times the square root of x, and g of x equals negative 9x to the 1/2. So another way to write that would be g of x equals negative 9 square root of x. So we're just talking about domain issues. The first one that we have to worry about, an even root, occurs right here. We've got the square root of x. So first thing it asks us for is the sum of f of x and g of x. So if we have 4x to the 1/2 plus negative 9x to the 1/2, it's just combining like terms since they're both x to the 1/2. We add their coefficients. So 4 plus negative 9 gives us negative 5x to the 1/2. Or in radical form, negative 5 square root of x. And so for the domain, because we have an even root, because we have a square root, the thing underneath has to stay positive. So the thing underneath is x. Positive means bigger than or equal to 0. So for our domain, x would have to be greater than or equal to 0. In interval notation, that's bracket 0 to show that we can equal 0 to infinity. Second one, number 2, f of x minus g of x. So same idea, only now we are going to subtract them. So you have 4x to the 1/2 minus negative 9x to the 1/2. Well, minus and minus turns into plus, so we're really doing 4x to the 1/2 plus 9x to the 1/2. And so, again, they're like terms since they're both x to the 1/2, so you add the coefficients, and you'll get 13x to the 1/2, or 13 times the square root of x. And again, the same issue applies. We've got an even root, so what's underneath has to stay positive. So the thing underneath is x, has to stay greater than or equal to 0. So that means bracket 0, since we can equal it, and we'll count up and use all the values from there to infinity. Remember, infinity and negative infinity always get the rounded parentheses. We can never equal them. All right, so the next one says f of x times g of x. We're going to find the following. So if f of x is 6x times x to the 3/4, well, we know it's 6. For the x's, when you multiply the same base, you add your exponents. So 1 plus 3/4 would be 1 3/4, or is an improper fraction. That's 7/4, because remember 1 would be 4/4. So 4/4 plus 3/4 gives you 7/4, or 6x 1 3/4. If we put it in radical form, so the x to the first would be on the outside, and then you've got x to the 3/4 left. So that would be the 4th root of x to the 3rd power. But again, we've got an even root. So again, the thing underneath has to stay positive. So x cubed has to stay greater than or equal to 0. Well, if we cube root both sides, we get x has to be greater than or equal to 0, just like the other ones we did. It's not always just x, but in these couple examples it was. So we start at 0 with the bracket and go up to infinity. Now for division, again, we set it up as a fraction. So f of x is 6x, g of x is x to the 3/4. And so now, 6 divided by 1, since x to the 3/4 doesn't have a coefficient, it's just a 1. 6 divided by 1 is 6. And you subtract your exponents. So in the top, since it doesn't have an exponent, it's a 1. We can think of 1 as 4/4. Try that again. So it's x to the first. 4/4 is the same as 1. And now I have a common denominator to be able to subtract my exponents. So 4/4 minus 3/4 gives me 1/4. Or in radical notation, that's the 4th root of x to the first. And again, an even root. So the thing under that even root, in this case is x, has to stay positive, bigger than or equal to 0. So our domain, we can use 0, and then we're going to use everything larger than that, all the positive. Last thing we're talking about is composition of functions, and this is a form of substitution. we're going to take one function and substitute it into another function. So in place of the x in this function, we'll plug in this other function. So we get rid of the x when we substitute and put a value in place of it. In this case, instead of a single number or variable, it's going to be a whole expression. So this first example has numbers involved. It says g of f of 3. So we're going to take 3, plug it into function f, and then plug that value into function g. So function f says 2 times some input minus 7. So f of 3, 2 times 3 minus 7. So 2 times 3 is 6, minus 7 equals negative 1. So f of 3 equals negative 1. And now we're going to take that and plug it into function g. So we found f of 3. We found that that equals negative 1, so now we're going to plug that into g. So g of f of 3 is the same as g of negative 1 because we found out f of 3 was negative 1. So in function g, replace the x with negative 1. So negative 1 squared gives you 1, plus 4 gives you 5. So g of f of 3 equals 5. You can think of it kind of like an assembly line. You're doing multiple functions. So first we figured out f of 3, then we took what that was and we plugged it into the next one, which was function g, and we got our final answer. All right, so let's do it with whole expressions. So number 8 says f of g of x, or sorry, f of h of x. So function f, this time, when I don't have a number, I want to start with the outside one. So if I have a number, I started with the inside one. But if I have an expression, I'm going to start with the outside. So function f, I'm going to write this down, but I don't put the x because I'm going to substitute in place of it. So I put down a blank set of parentheses where the x was. So function f said sum input x plus 4. So blank, sum input plus 4. The input they want me to use is h of x. So I've got to take this h of x function and plug it in where the x had been in f of x. So h of x was 3x to the 1/2, which we know means 3 times the square root of x. And since I can't combine like terms, that's just going to be it. I'm just going to have 3 times the square root of x plus 4. So that's my final function for f of h of x. All I did was take function h, plug it into function x, plug it into function f of x in place of the x. And I didn't have like terms, so there was nothing to simplify. For my domain, though, I do have a square root, an even root, so the thing underneath, in this case the x, has to stay positive, bigger than or equal to 0, so my domain will be 0 to infinity. G of f of x, so I write down function g, it says 5 times some input squared minus 2. Again, I left a blank spot where this x would have been, so it's 5 blank spot squared minus 2. In the blank spot, I'm supposed to put f of x, which is x plus 4. So I bring this over, put it in here. I've got a binomial squared. I've got x plus 4 to the second power, so I've got to use a box to multiply that out, or FOIL if you prefer. You'll get x squared, 4x, 16. So you've got 5 times x squared plus 8x plus 16. Just adding up the contents of my box, and then I've got minus 2. So I distribute the 5, I get 5x squared plus 40x plus 80 minus the 2. So it's 5x squared plus 40x plus 78. That's my finished function for g of f of x. For a domain of this one, well, we don't have any even roots. We've got an even power. And then there's no division. So I don't have any of the two things that cause me to restrict my domain. So my domain is going to be everything, negative infinity to infinity, because I didn't have an even root like here, and I didn't have any division like we're going to have in this next problem. So there's no reason to restrict. That would just be the final answer there.